Can you hear me now?
Yes, sir.
Okay. And can you see my screen?
Yes.
Okay. Okay, then we'll start as usual. So, any doubt? First, we'll take doubts from this week and last week's lectures. Then we will go to solve problems of this week. So if there is no doubt right now, you can.
No, sir. Sir,
Yeah. Okay. Yeah, go
I
ahead.
have a doubt in single layer and double layer winding.
Okay.
So while calculating the voltage induced,
Hmm.
like in that N in the formula, na, root 2 pi F pi N.
Hmm.
So there was a problem that coil group and per phase voltage.
Okay.
So there is a confusion. Means what is the coil group? And how many coils I have to take for the per phase voltage?
Coil group it is not mentioned in the question.
No, it is written just per coil group.
Okay. Coil group is, see, it's on the number of poles. Say you have a 2-pole machine. So it's like this, you have one north pole and one south pole. So this is the minimum requirement for a motor, for a machine, right? The 2-pole is the smallest number of poles you can have. So here all the coils of a 2-pole machine, they form one coil group. Now if you have, say, more than 2 poles, in a multiple pole pair, suppose you have a 6-pole machine, that means, so it looks like this. So here every band form one group, each band forms one group. So all the coils that come under a pole pair, that would create one group like this.
It will be 180-degree out of phase, no, sir?
Who?
Like you have chosen the, so N will be like 180-degree out of phase.
Yes, these two,
So
this and this. And that is how they are connected, right? So if you have one coil, one side of a coil here, another side of a coil here, then the current, say if it is going out, it is going in, and they are connected in this fashion. So ultimately you get the addition.
so number of turns is like 5.
Hmm.
Z equal to 5.
Hmm.
And it is a double layer winding.
Okay.
So what will be my N?
Number of coil groups you are asking?
Yeah.
Wouldn't that depend on the number of pole? Just a minute. Are you asking about the N in EMF?
Yes, sir. That capital N.
See, say this is one coil like this. Okay. And here you have some conductors. You are saying 5 conductors, right? Now you have some more coils in the same pole pair. They are kind of in series, maybe in this way. So all of it, say in this case what I have drawn, all the conductors, they are coming in series. So 5 into 3. In the EMF equation, these two sides are already considered. The root 2 pi into flux per pole Fn kpkd. Here the EMF of both the sides are considered. Okay, so what you have to take is this N as number of turns times how many coils are there, 3 in the group.
In double layer,
I think it will come as the same.
in single layer, looks like single layer. But in double layers, conductors are 2 coils are in there in one slot.
Actually difficult without numbers. I think in this problem we will encounter such a scenario where we have to find out N. There we will see
Okay, sir. Okay.
towards the end. Without number it becomes difficult to imagine. We'll look at the end of this problem.
Okay.
Yeah. Anything else? What definition of coil group was given in the lecture videos?
Yes,
Do you
sir. It is
remember?
like number of coils under one pole.
One pole. Then this is not coil group. If it is one pole, then this much you have to take. Here now it's making sense from the problem also. Then this is one coil group. So if this one comes under the north pole, this side, this one will come under the south pole, the other side of the same coil.
Yes, sir.
So again, one coil cannot be completely under one pole, right? So basically coil group comes out to be the coil side group. So these sides, this side, this side, this side, they form one coil group. 5 into 3 is the N.
Okay, sir.
We'll see at the end of this problem, there is one step where we have to find out capital N. There we will find out. Okay. Any more doubt? Okay, if not, then we will start with this problem. So there is one set of data today, and based on that, some 11 questions are there which we will solve. All the formulae that are necessary for this problem are derived in the lectures. So for derivation, you can refer to the lectures. Okay. So a 6-pole 3-phase 50 Hz generator has an active length of 0.4 meter, diameter of 0.48 meter, 72 slots, 60 degrees phase spread, double layer winding. Assume air gap flux density to be sinusoidal with Bmax 0.7 Tesla. Coils have 5 turns each, and are short corded by 1 slots. So, any doubt regarding the terminologies used in this question? Okay. So in total, how many coil does the stator have? So 72 slots are there, and it's double layer. So double layer means there is one go side, one return side, one go side, one return side of two separate coils, not the same coil, of two separate coils. So 72 slots and a total of 2 into 2. So these many sides, and one coil has 2 sides. So basically, for a double layer winding, as many slots, that many coils in total. So total 72 coils are there in this winding. Okay. Okay. So going ahead, slots are numbered from 1 to 72. One side of a particular coil is in slot number 5. If the other side of that coil is not in slot number 16, then in which slot should it be? Okay. So 72 slots are there in total. 72 slots and 6 poles. So 72 slots, 6 poles, that means 12 slot per pole, right? So if there are 12 slots per pole, then if I have one side of a coil in slot number 1, say the go side is in slot number 1, it should come back at the 12th slot. Similarly, the next one, 2, should come back at 13th slot. But the question says that it is short corded by one slot. So this diagram is for full pitch winding. Now for short pitch winding, here the short cording is by one slot. So if it goes from slot number 1, it comes one slot before. So from 11 it comes back. So no, sorry, I made one mistake here. 12 slot per pole. So north pole will have 1 to 12 north pole, and south pole starts from 13 to 24 is the south pole. So if it is full pitched winding, if it is going through 1, it comes back in 13, not 12. Comes back in 13. And slot number 2 comes back in 14. That is for full pitch. Now it is short corded by one slot, so it is now coming back in 12. That is, if it is going from slot number n, it will be returning from slot number n plus 11. That's what we will be expecting. So one side of a particular coil is in slot number 5. So we are expecting it to come back from slot number 16. But it says that the other one is not in slot number 16. So basically, what is happening is it's numbered the other way. We have assumed it's numbered in this way. It's numbered the other way. Or you may say that it's owned in the other way. So we
66, sir.
66, yes. So basically, instead of doing 1 plus 11, sorry, it is 5 here. So 5 plus 11, that is what we were expecting, but it is not found. So it has to be 5 minus 11, that is minus 6. Minus 6 means, so there are 72 slots to the other way. So basically 72 minus 6, 66. If you find it difficult to visualize, you can simply think like this. You keep on counting like this, 66, 67, this way, 72, again 1, 2, 3. So in this fashion, 72 becomes 0, 71 becomes minus 1, and 66 becomes minus 6. So it goes in this, goes from slot number 1 and comes back in slot number 66. Okay. Find the slot pitch in electrical degrees. So slot pitch is simply if you have, say, these are repeating like this, that tooth, they're repeating like this. You can calculate in whatever way you want, or you can measure in whatever way you want. You can measure this direction, distance. You can measure this distance. You can measure from middle of one slot to middle of another slot. This distance, whatever, you will get the same thing, slot pitch. So basically there are 72 slots. So 360 degree by 72. This much is the beta, but that is in mechanical degrees, because 360 degrees is a total mechanical angle. So this. Now we know that theta electrical equals P by 2 theta mechanical. So to get it in electrical degree, you have to multiply it with 3. 6 by 2, 6 pole machine. So it becomes how much? 360 by 24. It is 15. So 15-degree electrical is the slot pitch in electrical degrees. Any doubt? If not, then we will go to the next question. Find the rated speed in RPM. There is a little bit inaccuracy, you can say. It's not mentioned which machine, but since no other data is given to us, we can simply take the rated speed to be synchronous speed. That is 120 F by P. 50 Hz is given. 1000 RPM. Okay, so find the value of flux per pole in milliweber, assuming the air gap flux distribution to be sinusoidal. The flux per pole is, say, if you cut the machine and lay it flat, they're saying the air gap flux distribution to be sinusoidal. You will see that the air gap flux distribution, flux density distribution looks like this. Okay, pure sinusoid. This. Now, how much is one pole? This much is one pole. This much is one pole. Okay. One complete sinusoid would make one pole pair. That is one unit of the machine. That is the smallest unit of a machine. So how to find out the flux per pole? Basically, you take infinitesimal area in the air gap. So if this is the machine, you take infinitesimal area on the air gap. Infinitesimal area will be like this. If it is d theta, infinitesimal angle, then, and this is radius r. So r d theta times L. L is the stack length or active length of the machine in this direction. L, this much, times B. B, which is a function of theta. It is varying with theta. B is a function of theta. So area times flux density gives you the flux. Only thing is, here we have taken theta as mechanical, this theta, whereas this B, you can take in whatever way you want though. Just make sure that you are not mixing up electrical and mechanical angles. Okay. Now, if you write B equals B sine theta, the B max sine theta, if you write B equals B max sine theta. Then what is happening is, you see, if this is 0, this becomes 360, right? So this theta is actually electrical. This theta is electrical, and this theta is mechanical. So you have to make this theta also electrical. So theta electrical is P by 2, theta mechanical. So you have to multiply a 2 by P. Now this theta is also electrical. So this is a flux per pole. Now if you integrate this over one pole, that is 0 to pi, what are you getting? This 2r gives you d. D is the diameter. D by P. L is a constant. Bm is constant. Sine theta d theta. Am I missing something here? One pi looks missing. No, it's okay. So
It's okay, sir.
So it's coming out to be dl by p bm. Sine theta, if you integrate, becomes minus cos theta. So it basically becomes cos 0 minus cos pi. Cos 0 is 1, cos pi is minus 1. So it becomes 1 plus 1, 2. 2. So this becomes the flux per pole. Now if you put the values, the values are given in the question. Make sure that you put all the values in SI. Here today everything is given in SI meter. So we can simply put the values. 2 times D is 0.48, L is 0.4, Bm is 0.7 divided by 6 number of poles. This should give you some 44.8 milliweber. Okay, this is how we find out flux per pole. Sometime you may also encounter one terminology, that is average flux density, average air gap flux density. See, air gap flux density is a sinusoidal, so average will be 0. But whenever we are talking about the average of any pure AC waveform, what we actually mean is average of the positive half cycle. Okay, so average air gap flux density means average of this much. Now, so basically what is happening is average of a sine is this. It is 2 by pi. 2 by pi times the peak times the amplitude. So 2 times the peak flux density by pi, that is the average flux density, average area flux density. This is understood, means whenever someone is saying average of a sinusoid, that means average of the positive half, one positive half cycle. Okay. Now we look into find the pitch factor. Pitch factor, basically these factors, two factors we will see today in this class or lecture. One is pitch factor, one is mm, distribution factor. These are basically how to say tools to make your calculations easier. That is several reductions come in the total induced EMF because of distribution and because of the pitch. Once you find the once you know how to find the reduction factor, you simply multiply it with the value. Okay, so pitch factor, why does pitch factor arrive? Pitch factor arrives because we shortcut to reduce the harmonic. So ideally, what is the case? Ideally, if this is the air gap flux density distribution, so if this is the air gap flux density distribution, see this is a half-wave symmetric waveform. Half-wave symmetric waveform means value of f at theta equals minus of value of f theta plus pi. Okay, so if you have a coil here at some theta, and if you have, so you have the other side of the coil at theta plus phi, that is under the other pole but at similar magnetic flux density distribution. So whatever EMF this coil end sees, E, similar EMF this coil should also see, E. And what you get at the coil end is E plus E to E. But now if it is short corded, this one is no more at theta plus pi, rather it is a theta plus pi minus some short cording angle sigma or epsilon, epsilon. Now how much is epsilon? The question says it is short corded by one slot. Short corded by one slot. So one slot. Okay, we are doing all the calculations in electrical. Otherwise, we have to keep on converting every time. Okay, since electrical one pole pair, as I said, is the smallest possible unit, we will do all the calculation in electrical, which is also equivalent to mechanical calculation of a two pole machine. So we found out that beta in electrical, that is slot pitch, is 15 degree. So here that is, since it is short corded by one slot, that is also sigma, 15 electrical degrees. So what used to happen when there was no short cording? When there was no short cording, say if this is the EMF waveform, EMF vector, say the going side of the coil, this one, the going side of the coil, we'll draw it black, and this is the coming side, return side, go side, return side. We know that they get add up. So if this is the one and go side E and E, so finally what we get is E vector minus E vector. That gives us basically 2E, right? We cannot call this E, both of them E. Let us write E1 and E2. So E1 minus E2 gives us E2E1. E1 and E2 are equal in magnitude. Like this. But now E2 does not reside here anymore. It has been short corded. So E2 resides sigma away here. This is sigma. So now what you have to do, just simple, like before last time I did not draw the other one, minus E2. Then you have to find out the vector addition of this E1 and minus E2. Vector addition is, we know that A1 square, sorry, A square plus B square plus 2AB cos theta. Now in this case, A is equal to B. So it becomes, let me see if I can derive, I don't know. So if A is equal to, magnitude wise they are same, but there is one angle. So 2 A can be taken as common. What is 1 plus cos theta? 2 cos squared theta by 2, is it? Let me replace all the A's by E. Let me call this E. So previously, the voltage magnitude that we were getting is 2E. Now, because of the short cording, the magnitude that we are getting is 2E cos, okay, I wrote theta, it's sigma by 2. So basically, you have to multiply this factor if it is short corded by an angle of sigma. Not sigma. What did I say? Epsilon. So this is the factor that you have to multiply. So this is the pitch factor Kp cos sigma by 2. So in this case, it is cos 7.5 degree. Any doubt here? This pitch factor distribution factor is all about vector addition. You have to simply do vector addition by geometry. You will get all the formulae. This harmonic question we'll take later. We'll quickly do the distribution factor since we are already in the vector addition thing. Distribution factor, why does it come? First of all, see, pitch factor comes because we are short cording, so there is some deviation from the ideal voltage induced EMF that we would expect. Similar is the case for distribution factor. One pole pair has several windings. Okay, one pole pair has several windings. Again, we will draw, sorry, so not several coils. One pole pair has several coils. So if this is the air gap flux density distribution, I'm just drawing for one pole pair. My sinusoids are never symmetric. So like this, one is here. Say this black coil is here. The green coil is after one slot. The red coil comes after one slot, one more slot. So at the end, the EMF that is induced in all these coils say the black coil EMF, if it is like this, the green coil also gets the same EMF, but it is lagging. Similarly for the red coil. Now all these coils, they are connected in series. All these coils, they are connected in series. So if this phase shift is, let us say, theta, then the total EMF that we are getting at the end is, say, E sin omega t for coil 1, then E sin omega t minus theta, let us say, for coil 2, E sin omega t minus 2 theta for coil 3. This way it keeps going, as many coils are there. Okay. Now vectorially, if we see, we know that this kind of problems we can solve in phasor diagram or vectors. So if it is, say, E for coil 1, for coil 2, so it lags by theta. Okay, so let us find out what is theta. I said it is after one slot. We know that slot pitch is beta, that we have already calculated. So let us write beta directly from now on. Beta. Beta. Again, the next one is lagging by this beta. In this way, say some coils are there, this number of, so all the vectors are equal in length. Okay, although I'm drawing in this way, all the vectors equal in length. See, I have written E everywhere, E, because they are seeing the same same flux density distribution, only shifted in time. So the resultant that you get is this. So if you simply multiply, if you simply write NE equal to E, that is not true, because there is some shift that you have to consider. So one factor comes into picture, that is the distribution factor, KD. So KD is the ratio of, if we could put all the coils in the same slot, then we could have written E equals E plus E plus E plus, so NE, N times E. But the deviation from that idealistic situation is taken care by KD. Okay, like it was taken care by the slot, by the short chording factor, pitch factor, this way. Now you can have some geometrical calculation here. It's shown in the lecture. I'm not going through it. What you will get is KD comes out to be sine n beta by 2 by n sine beta by 2, where n is the slots per pole per phase SPP. This SPP we very commonly use, which means slot. SPP is not slot per pole, okay, though it looks like that. Slot per pole per phase. The slot is pole is. So in this case, what is SPP? 72 slot per 6 pole machine phase machine 4, and beta is 15 degree. So we know n equals 4, beta is 15, and yes, known. So if you calculate from here, you will get some KD as 0.9577. These vectors are equal in length. Understandable? Okay. Now we'll quickly do this one which we left. There is something in the chat. Give short coded by 2 slots. Give or given, what are you asking? Is it given by 2 slots? 1 slots. Shanti wrote something, but she has left the meeting. Anyway. Okay, so if there is third harmonic means thrice the frequency. So if you look at a two-pole machine, there are 2 lobes of a sinusoid, okay? Or maybe if you look at one pole pair of a multi-pole pair machine, one pole pair of a multi-pole pair machine, that is 1 unit. This one. Third harmonic is thrice the frequency. So when this fundamental completes, so 2 pole means that is a fundamental, okay? So when this fundamental completes 1 cycle, the third harmonic completes 3 cycles. So it should look like this. So here it completes 1.5 cycle, another 1.5 cycle. Let me draw it. Like this. So now the question is, what would have been the pitch factor for the third harmonic? Let us see if we can find out. Okay, I will first give you the formula. If it is say nth order harmonic, then pitch factor is given by cos n sigma by 2. Okay. So we found out its cos 7.5 degree before. So in this case, it will be cos 20.5 degree. That is the answer. Let us see if we can find out here. Suppose we had it here, theta. So what I am writing in black is the fundamental, and here we had theta plus pi. Suppose there is no short chording. You try to understand one thing here, that for, okay, let me copy this diagram. What went away? See one thing, this much is 360 degree for one wave, be it fundamental, be it any harmonic. This is a 360 degree. Okay, so you see, first you appreciate that if it is theta and theta plus pi for the fundamental, when there is no short chording, or if it is full pitch, let me write full pitch, when it is full pitch winding, then if it is theta and theta plus pi, the position of two sides of a coil with respect to fundamental, it is same for the third harmonic also. Can you appreciate that? See, look at the fundamental for this side of the coil, this side of the coil. Look at the fundamental, the blue one. It is going down. So it is theta plus pi for the fundamental. Okay. No, it cannot be theta plus pi for the third harmonic. It should be more. For this one, that is for the, sorry, theta and theta plus pi for the fundamental. For the third harmonic, this theta is actually 3 theta. This theta is actually 3 theta. Because when the fundamental is completing 180 degree, then the third harmonic is completing how much? 360 plus 180, 540 degree, 3 times. So 3 theta and 3 theta plus pi. So this factor 3 comes. So if you now short chord, one sigma comes here. So if I write like this, pi plus 3 theta. So one sigma comes here and one sigma comes here also, because mechanically they are the same. Mechanically you are keeping the slot just one, keeping the coil just one side, one slot before. So it becomes 3 times sigma plus theta. So this one propagates, and again if you do the same vector calculation, this one actually becomes 3 sigma, 3 epsilon. So n epsilon for nth harmonic, and it goes like this. Is it understandable? Why it is theta for the fundamental and 3 theta for the third harmonic?
Yes, sir.
Okay. So similarly, the distribution factor for the third harmonic, I will give you, so for, oh, I already wrote one n. Actually, this is m, this is not n. What I wrote here, m, this we traditionally write as m. M. So for nth order harmonic, distribution factor becomes just the angles you multiply with n. So sine nm beta by 2 by m comes out, m sine n beta by 2. So we did it before. Simply put the values and you should get something like 0.653. All the values are known. N is given as 3 and other values are taken from the last problem, M4 beta 15. Okay. All right. So RMS value of the EMF generated per coil group. So this is what I was saying that we will encounter at the end. Just a second. Okay, we will see. RMS value of the EMF in generated per coil group. So what do we have? We have 72 slots and 72 coils, 6 poles, and 5 turns in each coil. Okay. So first of all, we'll forget 6 poles because we'll take only one unit of the machine and do the calculations, because anyway we're talking about coil group. Later on we'll go for the whole machine. So first take one unit of the machine, that is one pole pair, that is 2 poles. So 2 poles, under those 2 poles we have 36 coils in total. Okay, 36 coils in total. Sorry, how can you 36? 2 poles, 72 coils, 72 by 3. How much is it? 24 coils under 2 poles. There are 3 units, so each of 2 poles, so 24 coils. Right? Now, it's a 3-phase machine. So this has, there are 3 phases. So in one phase, so 2 pole, how to write this? See, try to understand. I'm trying to make it sit north south. This is one unit. So there is one complete set of 3-phase winding, and that complete set has 24 coils. Understood? 3-phase winding. So one phase, if we take one phase, has 8 coils. So one phase under one pole pair has 8 coils. Right? 8 coils. Now out of these 8 coils, 4, so 8 coils have 8 coil sides. Slot per pole per phase. Am I doing something wrong here? Slot per pole per phase came out with this.
So per phase we have already calculated, sir, 24.
No, that is not per phase. That is per pole pair. That is
But
per
it's a
pole
2-pole
pair.
machine.
Yes, so 24. No, 2 pole will have 3 phase, right? You can have a 2 pole 3-phase machine, right? So even if you have a 2 pole machine, there is a complete set of 3-phase winding. Now these 24 coils, there is one complete 3-phase. Now 3-phase, so every phase is 8 coil. So what should it be? There should be 8 coil side here and 8 coil side here. Slot per pole per phase is 4. Yes, so slot per pole per phase was 4. So since we have 8 coil sides here and every slot has 2 coil sides, so 4 into 2, 8, it's matching now. Okay, so 8 coil sides are here. Under every pole. Is it correct? Okay.
So that 24 coils per phase.
Not per phase, 24 coils in every 2 pole. Now, every 2 pole has one complete 3-phase winding. You forget this 6-pole machine. Forget this 6-pole machine. Suppose there is a 2-pole machine. There also you can have a 3-phase winding, right? It's the same thing. We are looking at this at one unit, 2 poles. So there is also a complete 3-phase winding. So these 24 coils, they constitute one complete 3-phase winding. 3-phase. Now every phase has then 8 coils. See, we calculated slot per pole per phase is 4. And it's a double layer winding. So 4 into 2 is 8. So coil side per pole per phase should be 8. See, it is matching. Coil side per pole per phase 8. Another thing is the EMF that they have calculated here. I don't know what they have assumed behind it. EMF RMS, that is root 2 pi into flux per pole into frequency, this N, capital N that we are discussing, Kp into Kd. Everything else is known here. Only thing is N, what it should be. N is definitely 5, that is number of turns, into coil sides. Should it be 8 or should it be 4? Should we calculate once? Say the EMF, if you look at this, the EMF of this coil here, EMF E, this is given by BL into V, right? Now BL V is R omega. Omega is radian per second. B, and B is instantaneous. If you write, then B sine omega t. So B max L R omega sine omega t. Now what was our expression for this flux? This is 2dl bm by p. 2 dl bm by p. Let me keep it different. 2 dl bm by p. Now this omega that we have kept here, it is mechanical. Okay, so you have to make it electrical, so it becomes 2 by p bm r l omega. It's mechanical sine omega t. Let's see if we can find out their assumptions. If so, then okay, something we can write from here. 2 into r becomes d. So d bml, this much we have taken, this we have taken by p. One more 2 we need, so 1/2 comes here, 1/2 comes here, times omega sine omega t. We are still calculating for one side. Okay, so one number of turns will come here, not capital N. So let us say small n is the number of, okay, I will let t turns. So this t will keep getting multiplied everywhere. Omega sine omega t. So it becomes 5 by 2. Omega is 2 pi f. Number of turns t. Sine omega t, we are still getting voltage of one coil side. So it becomes 2 goes out. 5 pi f, number of turns t, sine omega t. So RMS, if we find out, it becomes square root of 2 pi phi f 2 pi phi f t, right? And anyway, kd kp will be coming. Let me see how far we are from this. 2 pi phi f. Okay, so only thing, okay, kd kp we cannot write here. Understood. Times number of turns. Now whenever you are transforming from this number of turns, that is the number of turns of one coil side. Number of turns of one coil side. Now how many coil side do you have under one pole? Once you do that, then the concept of this vector group, vectors that come. So then it becomes 2 pi phi f t into n. N is the number of coil sides per pole. Coil sides per pole, n. Now the kd and kp comes into picture. So this is what they are calling capital N. This is what they are calling capital N. So N in this case becomes number of turns times number of coil side per pole per phase, which is 8. Can you see any mistake in this derivation? Let me know.
So n should be like 4 here.
Small n.
Yes.
Why?
Like 72 slots is 72 coils are there.
Okay.
And 6 pole are divided by phase 3.
That is coils per pole per phase.
Yes, sir.
Then why am I getting? Just a minute.
No, suppose you put R/P
Hmm.
on the seat. Just write R/P
Okay.
and write NS like 6 poles.
Okay.
No, in the vertical side, sir. When R
Like
will be
this.
having 6 poles, Y will be having 6 poles.
Hmm.
Now each N has 4 coils. N has 4, S has 4.
Just a minute. 6, 12. It should have 12, right? 12. Then for R, it should be 4. Yes.
4, 4, 4,
Okay.
4.
Okay. Okay. Yes. Yes. Yes.
And that will be for each phase.
Hmm.
So 6 into 4, 24, 24, 24.
72. Yes.
Yes.
Just a minute. Let me just check once what I am making mistake here. So this has 24. This has 24. It's 24. Okay. But 24 coils. Okay, not 24 coil sides. So 24 coils. So yes, R has 4 coils. No, sorry, R has 8 coils.
So sir, N is having 4. That is the confusion, sir.
Just a moment. So this N is has 1 coil. So every pole has 1 coil side, right? One side of a coil comes under 1 pole.
Yes, sir.
True. Now there are 24 coils under these 2 poles.
Yeah, like
Now per
there's a
phase, there are
4.
8 coils under these 2 poles per phase. 8 coils under these 2 poles. So 8 goes out from here and 8 comes back.
Yes.
Then 8, it should be 8, right, per phase.
Yes, sir. It's like a pole pair. We have to divide it by pole pair.
It's not that
So
north pole has 12 coils. No pole has 1 coil. They have coil sides. So until this, it is correct. One phase has 8 coils. Now, if one phase under this one pole pair has 8 coils, then 8 coil sides are on one, say, north pole, and 8 coil sides on south pole.
yes, sir. It looks like that.
This coil group terminology is confusing to me. I don't know. See, the equation that I derived here, this one, this is for one coil side. Just one coil side. That is, you can say that under one pole.
Yes, sir. We can do it 2 times. Then it will be for the coil.
It becomes for the coil. Oh, that's okay. That will do. Then that can be done. Then to multiply by 3, it becomes for the whole machine at the terminal that we get. That's fine. But this n value, coil group, I don't know what they meant by coil group. It looks like this much they said by one coil group under one pole. Let me just check if I missed any factor of 2 here. BLV is known, the number of turns we multiply. So 2 BLV RW or omega. I wrote it in terms of sine omega t. Then this mechanical became electrical, so 2 by P comes into play. Now just manipulating things here. This 2R became D. Another 2 we needed, so 1/2 came here. Then BM, L and P we had, so it became 5 by 2. Omega is 2 pi F. So 5 pi T. Looks correct to me. This is for one coil side. Is for one coil side. Now if you multiply with 2,
That becomes for the coil.
that becomes for the whole coil. Now there are several coils under one pole pair. Now as soon as you are considering all the coils under one pole pair, you have to also consider the distribution factor and the pitch factor. So if,
So, sir, this N is actually coil side only because you
yeah,
already
looks like that.
multiplied the 2.
Should be the coil
So,
side.
yeah, it is because already we have considered the coil, other side of the coil by doubling it.
Should be the coil side. So what we have here is basically coils per
Per
pole
pole per
pair.
phase.
Yes.
And
Or
RMS value
phase
will be
also.
1 by root 2.
Yeah, we haven't done RMS yet. No, this is instantaneous. Oh, RMS is 1 by root 2, right? I think there is
Yeah,
one.
it's sinusoidal, no?
There is one. Oh, then there is one term missing somewhere.
To flux.
Oh, now it is matching. Yeah, now it is matching. I'm
This is
just telling
matching.
you, it's matching now. Per phase. This times t times sine omega t. This gives you under one two-pole machine. This gives you one two-pole machine. So this 1 by root 2. So basically the RMS becomes 1 by root 2 times pi phi f number of turns times coil side under one pole coil sides under one pole times kd kp. Let me also write it down so that when you get the
And 2 times, sir. 2 times.
2 times where
It is for the single conductor, no? So on the other side, you have to take it to make 2 times.
coil. No, when they are saying coil group, they mean one pole, not one pole pair, one pole. So when you are talking about one pole, we can talk only about coil sides, not a complete coil.
Yes, sir.
True. One pole. So let me write like this. So for one phase under one pole, the total EMF RMS will be given by 1 by root 2 pi flux density, flux per pole, frequency, number of turns time n into kd into kp, where n here in this case will be, just refer to some textbook and find out what are the standard terminology for this, standard notation for this n and all, where n that we are writing here is the coil side per phase per pole. Confusion came because here I multiplied with root 2, it should be 1 by root 2. Now it's matching, everything is matching now. So in this case n is 8. See, it can be verified from here also. We found out that slot per pole per phase is 4. So slot per pole per phase, if it is 4, and if it is double layer winding, then coil side per pole per phase will be 4 into 2, 8. It should be 8.
Yes, sir.
If just put the values, you should get something like 188.9 volt. Okay, any more confusion here? I think everything is clear now.
Suppose that we use the original formula, na? That root 2 pi f pi n. So here this
What they have
this
done
n can be like
is,
4.
yes, basically this 1 by root 2, no, you make it 2 here. Basically 1 2 by 2 you do into 2 by 2. These 2 you send here, it becomes root 2, and this 2 that comes n by 2 and becomes 4. But I would suggest you to stick to this. Easily understandable. At least to me it is more easily understandable. What we are doing here is 1 by root 2 into 8. In the solution, what they have done is root 2 times 4. Same thing.
It is coming as 199, sir. No. 1 minute.
99.
No.
Root 2 pi 5 we took from that.
KPKD, I think.
Kp should be 0.991.
Yes, sir. Correct.
Yeah. Okay, others. I cannot see who are the participants today. I'm using another setup. Okay, it's good that we had this confusion and I eventually ended up doing the whole derivation for the how to say this thing, this CMF value, and every term is now clear. This is why I told. Now, if we do the derivation, we can find out where they have taken some assumption, some terminology, because at the end we have the raw data with us. Number of slot, number of coil. Even if we do not know any term, we can find out the voltage. That is why we directly went for the derivation, because there we know what we are assuming as what. Okay. So we did it for one coil group. Coil group, as I said here, is under one pole. So the total will be this times number of pole. Whatever you get. Some approximation I did, this should not be equal to this. Okay, that's a good discussion today, quite interactive. For me also a lot of confusion got cleared. Okay, that's all problems for today. So if there is any more discussion, we will do. If you guys are having any confusion here, you can ask me, or I would suggest you better go through this. You better do yourself once. In the lectures also derivations are done, but you yourself do. KDKP multiplication you must have understood. You might have understood. If not, ask me. Not difficult, just how much is the deviation. You cannot put all the coils in the same slot. So if you could put all the coils in the same slot, then the vectors would look like this. Vectors would look like this. And what you get is as many, say I have written 1 2 3 4 5, so it becomes 5 times E. 5 times E total. But we cannot. So it becomes something like this. Definitely this is smaller than 5 times C. That is why KD is always less than 1. So this is something, say some KD times 5 times C. Definitely KD has to be less than 1. Why? Because we cannot put all the coils in the same slot. Just one thing. You can ask me if you want to ask anything.
So how they calculate a neutral voltage?
Sorry?
Phase to neutral.
Phase to neutral. It depends. It means if you have 3 coils, how they are connected. So 3 coils are there. Most of the case, what you will get is simply you will get these 3 terminals outside. If it is star connected inside, and they give you the star point also, You can find out the phase to neutral. You have to have the star point outside. If not, one very crude method is there. That is, you put very high values of resistance so that there is not much voltage, not much current is flowing, and you connect them like this, find out the voltage, and anyway we have the formula.
Yes, sir. That, but how they connect the winding?
Winding, how do they connect? Inside they see, windings are insulated. Now where they have to join, say they keep on doing the winding in the wires, and at the end when they have to join, they um, remove the, what is that called, remove the insulation. You can remove the insulation by simply using a blade. Just scratch on it, the insulation gets removed, enamel insulation, and shiny copper comes out. Then there you can use solder or tape. I think solder do they use, I don't know, but solder can be used. Then finally you get one wire outside the machine. Maybe after some months I will get to know very well how they do, because my machine is now being fabricated. Let me see. Let me see if there is a good photo. Some photo I got. See, look at this white portion. These are the places where they made the connection. And ultimately you get out the white, this red black where you are getting. Here they are making the connection. They remove the insulation there and then join the copper. I think here if you see, they have removed the wire insulation. Looks like that. Not very clear though.
Yes, sir. They internally connected.
Mm-hmm. Then are you asking about something else?
And what may be the like insulation level? It's 1
That
kV.
depends on the voltage level.
Or their simple
7.
enamel.
There are classes of insulators now. I do not remember what is required for what. The voltage level and the temperature, operating temperature that you need, that decides. Turn to turn voltage and operating temperature.
Okay, sir.
Classes
Thanks a
of
lot.
insulations, if you see there, you will get that.
Okay, thanks a lot.
Or you can see some machine design book there, they can have a chart, and some handbook may help. Okay, for the record, I took this from Google, from some website, not mine. Okay, we'll wait until 8:45 maybe. After that, I will stop the session.
How you measure the temperature of the motor?
Nowadays, there are thermal cameras.
Like for tripping something, some short
Are you
circuit
saying
tripping.
online measurement?
Yeah, online.
See, if it is that critical, you can have temperature sensors inside the motor. In general, it's the other way around. It's designed so that it's always mm, inside the safe temperature range. But still, if you need thermal protection, then you can have sensors inside. There are some innovative indirect ways of mm, finding the magnet temperatures also. To find out the voltage, then correlate with the magnet characteristic to find out how much the magnet temperature is. One of my colleagues did.
The core temperature.
Core temperature, anyway, the outside is available to you. Core temperature generally, as far as I know, is not a matter. Mostly we are bothered about winding temperature and magnet temperature. Core temperature doesn't go up that much that it will harm. Does it go? I may be wrong though, but I see what
Short circuit condition.
short circuit condition, your winding will burn, and your magnets may burn, may demagnetize completely. Short circuit, see, high current will not increase the code that much. If there is high amount of alternating current flowing continuously, that will increase the core loss. But before that, it will trip due to short circuit, not due to the core temperature increment. Core loss is that is proportional to B and F, right? And to some factors, B squared, F to the power 1.6 and all, or B to the power 1.6 again. So high frequency core temperature might rise, but generally if you are going for high speed, the flux is reduced, the field weakening. In general, I have not seen people bothering about core temperature. People are mostly bothered about winding and um, magnet temperature.
Yes, sir.
So someone else is in the meeting. Niraimati, are you there? Here it is showing the meeting is running for 9 hours. I think he or she joined some 7 hours back and did not leave the meeting. Anyway. Okay, then we'll stop for today. Next Monday again, 7 p.m. we will meet. Next day, I think we'll go into induction machine or some. I don't know whether there is something else. So just let me check what is the topic for next day. Oh, again, double layer winding table for three-phase distributed winding table. Introduction to rotating magnetic field. So to some extent, induction machine. Induction and synchronous also both are related to this. So what kind of questions will we cover? Winding table and winding connection. Okay, so once again, winding. next day. Okay, we'll meet next Monday. Thank you.
Okay, thank you.